Chapter 2, Neuromuscular Anatomy and Adaptations to Conditioning. One of the major goals of the strength and conditioning professional is to provide conditioning programs for athletes that will increase muscular strength and power. Central to this goal is a sound understanding of basic anatomy and physiology of the neuromuscular system. Equally important is knowing what adaptations occur in the neuromuscular system as a result of different programs, because the nature of the athletic event determines the type of conditioning that should be undertaken to achieve the desired response. Accordingly, this chapter presents basic information on the fundamental unit of the human neuromuscular system, the motor unit, describes motor unit control, and explains the importance of proprioceptors. It then explains the basic adaptations to the neuromuscular system to different modes of training, with special reference to skeletal muscle. Neuromuscular anatomy and physiology. As noted in Chapter 1, skeletal muscles are composed of thousands of individual cells called muscle fibers, held together with a network of connective tissue that fuses and becomes continuous with the dense connective tissue of the tendon of the muscle. Tendons serve to connect skeletal muscle to bone. It is through this connection that muscle, by actively changing its length, produces force and brings about limb movement. Activation of muscles. Muscle fibers are innervated by motor neurons that transmit an electrical chemical signal from the spinal cord to the muscle. A motor neuron generally has numerous terminal branches and thus innervates many different muscle fibers. When a motor neuron fires, all the fibers that it serves are simultaneously activated and develop force. A motor neuron and all the muscle fibers that it innervates are referred to as a motor unit. The basic functional entity of muscular activity. The extent of control of a muscle depends on the number of muscle fibers within each motor unit. Muscles that must function with great precision, such as eye muscles, may have motor units with as few as one muscle fiber per motor neuron. Changes in the number of active motor units in these small muscles can produce the extremely fine gradations in force that are necessary for precise movements of the eyeball. In contrast, the quadricep muscle group, which moves the leg with much less precision, may have several hundred fibers served by one motor neuron. The action potential, electrical current, that flows along a motor neuron is not capable of directly exciting muscle fibers. Instead, the motor neuron excites the muscle fibers that it innervates by chemical transmission. Arrival of an action potential at the nerve terminal causes release of a chemical, acetylcholine, which diffuses across the neuromuscular junction, causing excitation of the sarcolemma. Once a sufficient amount of acetylcholine is released, an action potential is generated across the sarcolemma, and the fiber contracts. All of the muscle fibers in the motor unit contract and develop force at the same time. There is no such thing as a motor neuron stimulus that causes only some of the fibers to contract. Similarly, a stronger action potential cannot result in a stronger contraction. This phenomenon is known as the all or none principle. It is analogous to firing a gun. Once a sufficient amount of pressure is placed on the trigger, the gun fires. However, squeezing the trigger harder will not cause the bullet to go faster. Each action potential traveling down a motor neuron results in a short period of activation of the muscle fibers within the motor unit. This is referred to as a twitch. Activation of the sarcolemma results in the release of calcium within the fiber, and contraction proceeds as described in the previous chapters. Force develops if there is resistance to the pulling interaction of actin and myosin filaments. Although calcium released during a twitch is sufficient to allow optimal activation of actin and myosin, and thereby maximal force of the fibers, calcium is removed before the force reaches its maximum, and the muscle relaxes. If a second twitch is elicited from the motor unit before the fibers completely relax, force from the two twitches summates, and the resulting force is greater than that produced by a single twitch. Decreasing the time interval between the twitches results in a greater summation of force. The stimuli may be delivered at so high a frequency that the twitches begin to merge and even completely fuse, a condition called tetanus. This is the maximal amount of force the motor unit can develop. Muscle fiber types. Skeletal muscles are composed of fibers that have markedly different morphological and physiological characteristics. These differences have led to several different systems of classification based on a variety of criteria. The most familiar approach is to classify fibers according to twitch time, employing the terms slow twitch and fast twitch. Because motor units is composed of muscle fibers that are of the same type, it can also be designated using the same classification system. A fast twitch motor unit is one that develops force rapidly. It also relaxes rapidly and thus has a short twitch time. Slow twitch motor units, in contrast, develop force and relax slowly and have a long twitch time. A common classification scheme based on histochemical characteristics refers to slow twitch and fast twitch motor units as type 1 and type 2. The contrast in mechanical characteristics is accomplished by a distinct difference in the ability of the fibers to demand and supply energy for contraction, and thus to withstand fatigue. Type 1 fibers are generally fatigue resistant and have a high capacity for aerobic energy supply, but they have limited potential for rapid force development as characterized by slow actomyosin, myofibril, and ATPase activity and low anaerobic power. Type 2 motor units are essentially the opposite, characterized by fatigability, low aerobic power, rapid force development, high actomyosin and myofibril ATPase activity, and high anaerobic power. Type 2 muscles can also be classified into subdivisions, type 2A and type 2B fibers, differ mainly in their capacity for aerobic oxidative energy supply. Type 2A fibers, for example, have greater capacity for aerobic metabolism and more capillaries surrounding them than type 2B, and therefore show greater resistance to fatigue. Based on these differences, it is not surprising that postural muscles, such as the soleus, have a high composition of type 1 fibers, whereas large so-called locomotor muscles, such as the quadriceps groups, have a mixture of both type 1 and type 2 fibers to enable both low and high power output activities, such as jogging, sprinting, respectively. Motor units are composed of muscle fibers with specific morphological and physiological characteristics that determine their functional capability. Motor unit recruitment patterns during exercise. The force output of a muscle can vary over a wide range of gradation that is essentially for smooth, coordinated patterns of movement. Muscular force can be graded in two ways. One is by varying the frequency of activation. If a motor unit is activated once, the twitch that arises does not produce a great deal of force. Increasing the frequency of activation so that the twitch forces are allowed to summate, however, results in greater force development by the motor unit. This method of varying force output is generally used in small muscles such as those of the hand. Even at low forces, most of the motor units are activated, albeit at a low frequency. Force output of the whole muscle is intensified by increasing the frequency of firing of the individual motor units. The other means of achieving an increase in force is varying the number of motor units activated in a process known as recruitment. In large muscles, such as those of the thigh, motor units are activated at near tetanic frequency when called on, increasing in force output and achieved by recruiting additional motor units. The type of motor unit recruited for a given activity is determined by its physiological characteristics. For activities such as distance running, slow twitch motor units are engaged to take advantage of their remarkable endurance capability and resistance to fatigue. And if additional force is needed, as in a sprint at the end of the race, the fast twitch motor units are called into play in an increase in pace. Unfortunately, exercise at such intensity cannot be maintained for long. If the activity requires near maximal performance, such as in a power clean, most of the motor units are called into play, with fast twitch units, especially type 2B fibers, making the more significant contribution to the effort. Complete activation of the available motor neuron pool is probably not possible in untrained people. Although the large, fast-twitch units may be recruited, the effort is substantial. It is probably not possible to activate them at high enough frequency for maximal force output to be realized. The force output of a muscle can be varied by changing the number of activated motor units, or by changing the frequency of activation of individual motor units. Proprioception. Proprioceptors are specialized sensory receptors located within joints, muscles, tendons. Because these receptors are sensitive to pressure and tension, they relay information concerning muscle dynamics to the conscious and subconscious parts of the central nervous system. The brain is thus provided with information concerning kinesthetic senses, or conscious appreciation of the body in three-dimensional space. Most of these proprioceptive information, however, is preceded at subconscious levels. We do not have to dedicate conscious activity towards maintaining posture or position of our body parts. Proprioceptors are specialized sensory receptors that provide the central nervous system with the information needed to maintain muscle tone and perform complex coordinated movements. Muscle spindles are proprioceptors that consist of several modified muscle fibers enclosed in a sheath of connective tissue. These modified fibers are called intrafusal fibers, run parallel to the normal or extrafusal fibers. Muscle spindles provide information concerning muscle length and the rate of change in length. When the muscle lengthens, spindles are stretched. This deformation activates the sensory neuron of the spindle, which sends an impulse to the spinal cord where the synapse connects with motor neurons. This results in the activation of the motor neuron that innervates the same muscle. Spindles thus indicate the degree in which a muscle must be activated in order to overcome a given resistance. As a load increases, the muscle is stretched to a greater extent, and engagement of the muscle's spindles results in greater activation of the muscle. The more it's stretched, the more it activates. Muscles that perform precise movements have many spindles per unit of mass to help ensure exact control of their contractile activity. A simple example of muscle spindle activation is a knee jerk reflex. Tapping the tendon of the knee extensor muscle below the patella stretches the muscle spindles fibers. This causes activation of extrafusal muscle fibers in the same muscle. There is a knee jerk as these fibers actively shorten. This in turn shortens the intrafusal fibers and causes their discharge to cease. Golgi tendon organs. Golgi tendon organs, GTOs, are proprioceptors located in tendons near the myotendinous junction and are a series that is attached end to end with extrafusal muscle fibers. GTOs are activated when the tendon attached to the active muscle is stretched. As tendons in the muscle increase, discharge of the GTOs increase. This sensory neurons of the GTO synapse with an inhibitory interneuron of the spinal cord, which in turn synapses with and inhibits a motor neuron that serves the same muscle. The result is a reduction in tension within the muscle tendon. Thus, whereas muscle spindles facilitate activation of the muscle, neural input from GTOs inhibits muscle activation. The GTO's inhibitory process is thought to provide a protection mechanism from development of excess tension. The effect of GTOs is therefore minimal at low forces, but when an extremely heavy load is placed on the muscle, reflexive, inhibitory mediation of the GTOs causes the muscle to relax. The ability of the motor cortex to overcome the inhibition may be one of the fundamental adaptations to heavy resistance training.